Get ready to torque your nuts, harden your springs, and forge your mind into a bulletproof study guide. We are Mechanical Engineering Made Simple. Welcome back, Design Junkies, to Mechanical Engineering Made Simple. So today we're doing a bit of an industrial demolition job, you could say. We're tackling this long-held belief that lean manufacturing, the Toyota production system magic, only really works for nice, clean, discrete assembly lines.
Yeah, like making cars or appliances, things you can count easily.
Exactly. But our mission today, we're taking those core lean ideas and throwing them right into the deep end. We're talking huge-scale, continuous process industries, specifically steel manufacturing.
Think massive furnaces, liquid metal, stuff that's fundamentally different from building an engine piece by piece. We're talking about taking muta, waste elimination into environments where machines are gigantic, run nonstop, and you definitely can't just rearrange them over the weekend.
And it's interesting, isn't it? Lean came from scarcity. Post-WWI Japan, they had shortages of pretty much everything: capital, space, materials.
Right. So the whole philosophy was built around using less time, less inventory, less effort, but getting the same or even better output. Higher quality, more variety.
So the big question we're asking in this deep dive is, can that same scarcity-driven thinking really work when you're dealing with the sheer, overwhelming scale and inflexibility of heavy industry like steel?
That's the challenge. Let's dig in.
Okay, first, let's quickly level set on the difference between these two worlds. Discrete manufacturing, that's lean's home turf. You make things you can count: cars, phones, bolt.
Individual units, yeah. Whereas continuous process industries, they make stuff you measure or meter: oil, chemicals, cement.
Or in our case, steel, liquid steel flowing around.
Exactly. And historically, managers in these process industries, they've been pretty hesitant about lean tools.
Why is that? Just the scale?
Well, partly. You've got super high volume, but often very low product variety compared to discrete. And the equipment. It's massive, fixed in place. You can't just create a cell like you would in a car plant when your blast furnace weighs thousands of tons.
Right. Concepts like cellular manufacturing just seem impossible.
They do. And then there are the setup times, the changeovers. They can be incredibly long and costly.
That's a killer, I bet. You can't just swap a die in 5 minutes.
Not when changing over might mean shutting down a huge part of the continuous flow. We're talking potentially millions in lost production, maybe even risks to the equipment itself. So the traditional thinking is we need huge piles of inventory to buffer against these changeovers and potential downtime.
Okay, that makes sense from a risk perspective. But is that the whole story?
Well, here's the key insight from the research we looked at. Most of these so-called continuous processes, they're actually hybrids.
Hybrids? How so?
Think about that steel example. You have liquid steel, which is definitely continuous, flowing from the furnace through the caster.
Very measured flow.
But then what happens? Somewhere mid-process, usually after casting and maybe some initial rolling, that liquid metal becomes solid. It gets cut into discrete, countable units: slabs, coils, billets, whatever the form is.
So there's a point where it becomes discrete.
Exactly. It transitions from this non-discrete flow to countable pieces. And that specific point in the process, that transition, that's our opening. That's the toehold where we can start applying lean principles, even if the very start of the process remains continuous.
Interesting. So you don't try to force lean onto the blast furnace itself, but you find that discrete point downstream.
Precisely. You leverage that hybrid nature.
Okay, so if we found our entry point, the next step in lean is always identifying the waste, right? Muda.
Absolutely. The goal is always eliminating anything that doesn't add value from the customer's perspective. In heavy industry, you see all the classic wastes, but some really stand out. Inventory, obviously, given what we just discussed.
Those huge piles of coils or slabs just sitting there.
Yeah. Overproduction often goes hand in hand with that inventory. Defects, which can be incredibly costly when you're dealing with massive batches. And time-related waste, like those super long setup times we mentioned.
So how do you find it all? It must be hidden in plain sight sometimes.
The essential tool, really the starting point for any serious lean effort, is value stream mapping, VSM.
Right, not just a simple flowchart.
No, definitely not. VSM tracks everything. Material flow, yes, but also information flow, the orders, the schedules, and critically, it tracks time. How long does each step take? How long does material wait between steps? How much inventory accumulates?
It forces you to see the whole system, not just optimize one machine.
Exactly. You visualize the entire value stream from raw material to finished goods hitting the customer. And when the researchers applied VSM to this steel manufacturer, ABS, the results were, well, Pretty shocking.
Okay, let's hear it. What did the map reveal about their current state?
For their annealed product line, the total production lead time start to finish was 46 days.
46
Yeah.
days. That's incredible. Over a month and a half.
Yep. Now here's the kicker. They measured the actual value-added time, the time the steel was actually being heated, rolled, cut, treated, physically transformed.
Okay, how much was that?
5 days.
5 days of actual work out of 46 days total lead time.
Exactly. That means the value-added time was only about 11% of the total time the material spent in the system.
So for 41 days, roughly 89% of the time, that steel was just sitting.
As
And
inventory.
as inventory, waiting for the next process, waiting for a schedule change, waiting in a massive storage yard. And that right there exposed inventory as the single biggest source of waste and delay in their system.
And that much inventory, it must mask a ton of other problems.
Right, absolutely. It hides everything. Scheduling mistakes, doesn't matter, grab another coil from the pile, quality issues from the caster. By the time you find the defect, weeks later in the finishing mill, the conditions that caused it are long gone. Machine breakdowns, just work through the buffer inventory.
So reducing that inventory isn't just about saving space or capital. It's about forcing those underlying problems, the quality issues, the machine reliability, the scheduling hiccups, out into the open where you have to fix them.
That's the core principle. Inventory reduction reveals the rocks hidden beneath the water. Okay, so VSM shows a 46-day lead time, mostly waiting. How do you redesign this using lean for the future state? Where do you start?
You start by setting the pace. You need to link production directly to customer demand. That means calculating the takt time.
Takt time, the heartbeat of the system.
Yeah.
German word for rhythm.
Exactly. It tells you how often you need to produce one unit, in this case a coil, to meet customer demand exactly.
So for ABS, how did that calculation work?
Okay, the customer demand for this annealed product was 76,500 tons per month. You break that down, that's about 2,550 tons a day, which translates to roughly 127 coils per day, based on their average coil weight.
127 coils needed every single day.
Right. Then you look at the available work time. A standard day has 4,440 minutes, 24 hours times 60 minutes.
Got it. And the formula is?
Takt time equals available work time per day divided by customer demand per day.
So $1,440 minutes divided by 127 Ziller coils.
Which comes out to approximately $11.33 minutes per coil.
So the target is one finished coil needs to roll off the line every $11.33 minutes to keep up with demand. No more, no less.
That's the rhythm the finishing end needs to march to.
Okay, but here's the tricky part again. The front end, the blast furnace, the caster that's still continuous, right? It's pushing out steel constantly. How do you reconcile that push with this new $11 on 3-3-minute pull rhythm at the finishing end?
That's where the hybrid pull system design comes in. You acknowledge the front end has to push, at least to some extent. You can't just turn a blast furnace on and off based on an 11-minute cycle.
Definitely not.
So you strategically decouple. You designate one single point in the downstream discrete process as the pacemaker. This is the only point that gets a formal schedule based on customer orders.
And where was that for ABS?
In their future state map, it was the temper mill, basically the final processing step before shipping for this product. Everything upstream of the temper mill only produces to replenish what the temper mill consumes.
So the temper mill pulls from the steps before it.
Exactly. And those massive, uncontrolled inventory piles we talked about, they get replaced by small, controlled supermarkets.
Like a grocery store shelf, but for steel coils.
Sort of, yeah. You have a limited defined amount of inventory, maybe a few hours or a day's worth, not 41 days worth, held between key processes. When the downstream process, like the temper mill, withdraws a coil from its upstream supermarket, a signal, a Kanban, is sent back.
Like an empty slot on the shelf signaling, make one more.
Precisely. The Kanban tells the upstream process, okay, I've used one, now you can make one to replace it. It ensures you only produce what's actually needed when it's needed. It converts that push system into a pull system after the continuous part.
But you still need some buffer between the continuous hot end and the first supermarket, right? To absorb variations.
Yes, you manage that buffer carefully. It's calculated, not just accumulated. And importantly, you also need to level the production. Hajunka.
Leveling, meaning not making all of one type of coil on Monday, then all of another type on Tuesday.
Exactly. If your customer needs, say, 5 types of coils this week, you don't run huge batches of type A, then type B, etc. That creates massive swings and makes changeovers a nightmare. Hajunka means smoothing out the production mix.
So you'd make a little bit of each type more frequently.
Right. They introduced the concept of pitch, a regular timed interval for releasing small batches of work into the system. In the ABS future state, this was calculated to be around every $1.55 hours. Every 90 minutes, a small mixed batch of coils needed by the pacemaker would be authorized for production upstream.
So tack time sets the overall speed, Kanban supermarkets control inventory flow, and Hyjunka smooths out the mix. That sounds much more controlled.
It is, but making the system work relies heavily on the physical processes being stable and reliable. You can't have a pull system operating on an 11-minute cycle if your machines are breaking down randomly for hours.
Right. That smooth flow depends entirely on predictable uptime.
Which brings us to the technical fixes needed.
Absolutely. Tool number one has to be total productive maintenance, or TPM. You have to attack equipment reliability head-on. What was the problem at ABS? Just infrequent maintenance.
Partly, they had long scheduled shutdowns, like maybe furnace reline every couple of months, taking almost 1,000 minutes. But the real killer was the unplanned downtime. The study mentioned the caster's unplanned uptime followed an exponential distribution, specifically EXPO, open parenthesis, $20,160, close parenthesis, minutes.
EXPO, open parenthesis, $20,106, close parenthesis, minutes. What does that mean in practice?
It means, on average, it might run fine for about $20,160 minutes, which is roughly 14 days. But then it could fail unpredictably, and the downtime could last for several hours. That kind of variation just destroys a pull system.
So TPM aims to prevent those failures.
Yes. It shifts the focus from reactive, fix it when it breaks, or even just long-interval preventative maintenance to proactive and predictive maintenance. It involves operators and daily checks, cleaning, and lubrication. It means doing shorter, more frequent planned maintenance tasks to catch problems early. Maybe a 4-hour targeted maintenance every 3 weeks instead of that massive 10-hour shutdown every 2 months.
The goal being maximizing OEE, overall equipment effectiveness.
Exactly. Reducing breakdowns, minimizing minor stops and speed losses, making the machines reliable enough to support that tack time.
Okay, makes sense. What's tool number two?
Setup reduction, often called SMA single-minute exchange of dies, though it applies to any changeover.
Tackling those long changeover times we talked about. If you're running smaller leveled batches, thanks to Hyjunka, you must be doing changeovers much more often.
Way more often. If they take hours, the whole pull system collapses. SMAD's core idea is simple but powerful. Analyze every single step of a changeover.
And figure out what you can do before the machine actually stops.
Precisely. You separate internal setup tasks that absolutely must be done while the machine is stopped, like actually swapping a roll, from external setup tasks that can be done while the machine is still running, like getting the next roll ready, preparing tools, preheating things.
So find ways to convert internal time to external time.
That's the game. For the steel mill, they targeted things like the hot strip mill and the cold reduction mill, where work rolls might be changed, say, 18 times a day.
18 times. Okay, setup time is critical there.
Absolutely. So polishing the next roll, getting the tooling ready, placing hoses, all that needs to become external work happening concurrently while the current coil is running. You fight for every minute saved on those frequent changeovers.
Makes sense. Reliable machines, fast changeovers. What else?
The foundation. You can't forget 5S and visual system.
5S: sort, straighten, shine, or sweep, standardize, sustain. The housekeeping one.
It's way more than housekeeping, especially in a heavy industry. There's often this culture of, well, it's a steel mill, it's supposed to be dirty and cluttered. 5S directly combats that. Sorting gets rid of junk, straighten organizes tools and parts, shine keeps things clean, making abnormalities easier to spot.
Like an oil leak on a clean floor versus a dirty one.
Exactly. Systematize and standardize make it stick. It frees up space, improves safety, boosts morale, and actually helps quality by making problems visible.
In visual systems, what's an example there?
Things like clear floor markings for inventory locations. Or, in the ABS case, they proposed a simple visual Kanban post near the shipping dock. Instead of relying purely on computer systems or paperwork which can have delays or errors, this post visually showed the status and position of coils ready for shipment.
So a dock worker could instantly see, okay, this truck needs these 3 coils, and they are physically right here in these marked spots, and their status card is green.
Right. It reduces errors like shipping the wrong coil or one that hasn't passed final inspection. Simple visual cues to prevent mistakes and keep things flowing.
Okay, so we have the hybrid pull system design, supported by TPM for reliability, SMAD for quick changeovers, and 5S visual systems for foundation and error proofing. Did it work? What did the simulation show?
The researchers modeled this whole future state system using simulation software, Arena, I believe it was, to predict the impact.
And the bottom line, the lead time.
The results were pretty dramatic. The simulation showed that implementing the hybrid pull system, along with the improvements from TPM and SMAD, reduced the average production lead time from the original $34.2666 days they focused on in the detailed model.
Wait, wasn't it 46 days initially?
Ah, good catch. The initial VSM showed 46 days across the entire process observed. The simulation model likely focused on a specific, slightly narrower part of that stream for detail analysis, which had a baseline of $34.266 days. Still a very long time.
Okay, so from 34.26 days down
It's
to...
down to 12.12 days.
Wow, from over a month to under 2 weeks. That's almost a 65% reduction.
A massive improvement, yeah. Nearly two-thirds of the lead time just evaporated.
That's huge. What does that do to the value-added percentage? It was a dismal 11% before.
It jumped significantly. The simulation showed the value-added time as a percentage of total lead time increased to about 39%. Still room for improvement, sure, but a huge leap from 11%. Much less waiting, much more working.
So it really proves the point, doesn't it? Even in these massive, supposedly inflexible, continuous process industries, the core lean principles can be applied if you adapt them smartly.
It shows the constraint often isn't the giant machinery itself, but the management system, the scheduling, the inventory policies, the maintenance approach, the lack of flow synchronization.
That hybrid approach, finding that discrete point, seems key.
It's critical. You have to find that interface between the continuous push and the potential for discrete pull, and manage it with tools like supermarkets and Kanban.
It's a powerful demonstration that waste really is everywhere, even baked into industries we think of as inherently inefficient due to scale.
Right.
Continuous improvement is never really finished.
Absolutely not. And the next logical step, the real frontier for this kind of thinking in heavy industry.
Extending it beyond the plant walls.
Exactly.
Yeah.
Integrating the entire supply chain. Looking for waste not just inside the mill, but in the delivery of raw materials from suppliers and in the distribution network getting finished goods to the final customer. That's where the next big gains are likely hiding.
Fascinating stuff. Applying car factory thinking to melt shops and rolling mills and getting incredible results. Until the next equation, design junkies, we are mechanical engineering made simple. Stay balanced, stay precise, and never stop building.